Welcome to this series on the basics of orbital mechanics, where we are going to embark on a journey through the fundamental laws that govern the motion of celestial bodies and artificial satellites. Today, we start by diving directly into the heart of orbital mechanics with a closer look at Kepler's laws, the bedrock that spawned the field we are approaching together. Whether you're an aspiring aerospace engineer or just a curious mind eager to understand the universe, you're in the right place. Johannes Kepler, through meticulous observation and relentless curiosity, laid down 3 laws that describe the motion of planets around the Sun. These laws not only revolutionized our understanding of the cosmos, but also became the cornerstone of celestial mechanics. Today, as aerospace engineers, understanding these laws is crucial for everything from satellite deployment to deep space exploration. Even in their apparently simplistic formulation, the insight you can gain by truly understanding these laws is astonishing. Kepler's first law, or the Law of Ellipses, tells us that planets orbit the Sun in an elliptical path, with the Sun at one of the focal points. This law will be expanded on in the future and has only a general validity. As we will see, there are very important limit cases that expand on this concept, but this is a discussion for future videos. Unlike the perfect circles that were theorized from the time of Aristotle, this law introduces the concept of eccentricity, which describes how stretched out an orbit is. For aerospace engineers, the eccentricity of an orbit is a vital parameter in planning trajectories and understanding satellite paths around Earth or any other celestial body. Kepler's second law, or the law of equal areas, states that a line segment joining a planet and the Sun sweeps out equal areas during equal intervals of time. This means that a planet moves faster when it is closer to the Sun and slower when it is farther from the Sun. While not giving directly an easily applicable mathematical relation to describe the variation of velocity in an orbit, this law is particularly insightful for understanding orbital speed variations and is crucial for intuitively grasping most of the orbital maneuvers, ensuring efficiency and precision in space missions. Finally, Kepler's third law, the Harmonic Law, tells us that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. In simpler terms, the farther a planet is from the Sun, the longer it takes to complete an orbit. This law is a powerful tool for predicting the orbital period of satellites and understanding the dynamics of multiple body systems. It is also very useful to internalize the effect that the distance from the main body has on the period and velocity, an understanding very useful for aerospace engineering. Kepler's laws aren't just historical footnotes, they are actively used in today's aerospace engineering. These simple laws, while very basics and with little real predictive power, they are the base, the giant shoulder we are standing on. These laws were the reason why Isaac Newton decided to work on universal gravitation, his starting point. Today, everything we achieved in spaceflight, from designing satellite orbits to planning interplanetary missions, is all resting on the work of an uninterrupted chain of great thinkers, even if technically not the first in this chain. Surely Kepler is a key link in it that cannot be glossed over. One of the most important skills you need to have if you want to work in this field is a sort of sixth sense of what effect a particular maneuver would have on an orbit. Kepler's law are the way you can start developing that sense. Thank you for watching. This was the first video on a series going in depth about spaceflight mechanics. Next time we will cover the basic about Newton universal gravitation, and we'll define the central problem of our field. Thank you for joining us. Don't forget to like, subscribe, and turn on notifications for more explorations into the fascinating world of orbital mechanics. Until next time, keep reaching for the stars.